Thank you, Chris. Our next speaker is from the Massachusetts Institute of Technology, Kavli Institute for Astrophysics and Space Research. Please welcome Dr. George Riker, Principal Investigator for the TESS mission. George Riker, sorry.
Great. Well, thanks to everyone who's here today, and I'd like to also extend a thanks to all my family and close friends who've been hearing about TESS for the last 13 years. And today we're on the precipice of actually seeing the mission go, and tomorrow night things are hopefully going to be really even more exciting for us. So if I could have the first slide, I'll tell you a little bit about how TESS actually works, or at least the principle between the way in which it operates. And see, is this okay? All right. Well, this represents the group of people who, or at least the group of organizations who've put in more than 1 million person hours of work on this mission since the mid 2000s and growing as we went to the launch that we're coming up with. There's more than 12 universities and research institutes that are part of our team. So this is the basic idea behind TESS in terms of how it works. It's called a transit, and basically it occurs because nature has given us a number of systems, a few percent of planets that actually orbit in planes that happen to be along our line of sight. And as you could see from the animation that just went past, that small planets make small dips, big planets make big dips. And TESS will be sensitive to both types of planets, ranging in size from planets the size of the Earth, or perhaps even Mars, even smaller, all the way up to what we call super Earths. These are planets that we don't happen to have one like in our solar system, that are 1.5 or 2 times the size of the Earth, to planets that are the size of Neptune and even Saturn and Jupiter. So there's a whole range of planets that we know are out there, and the purpose of TESS is to basically go out and find them. And once we've found them, they can actually be the subject of follow-up observations that'll be studied carefully in the way that Chris was mentioning previously, especially the James Webb Telescope, but also future telescopes that many astronomers are working on in terms of optimizing the way that we can actually, for the first time, study atmospheres that are associated with these planets and look for potential biomarkers like oxygen or methane or CO2 that might be in the atmospheres and indicate biogenic activity. Okay, so then this is a representation of what we think TESS will be able to see in terms of planets. The little red dots are the planets for which we're going to have 2-minute resolution, and we've gone through and cherry-picked a set of about 200,000 candidate stars that we're pretty sure are going to have planets associated with them. A certain fraction of those will. The ones that have their planets in a plane that produces transits. The little blue dots, and there's so many of them it's really hard to see. There are 20 million stars that we're going to examine with a slightly longer time scale, but still short enough that we can actually see the transits. And with that set, we're doing a completely unbiased search. In fact, the search that we're doing will also include not only 20 million stars, but it'll probably include 10 million galaxies with very high levels of precision. And then for another 100 million to 1 billion objects, there are going to be measurements that can actually indicate brightenings of objects that can even lie in other galaxies or very, very far from where we are, supernovae, hypernovae, even coalescing neutron stars, which can produce gravitational radiation. So there's a whole variety of things that TESS will actually be able to do. So this is the other thing that you'll notice in this picture is there's a concentration of red dots at the South Pole and at the North Pole, and that's by design because those are the areas that the Webb telescope can actually look at any time of year. So we actually made the satellite in the way that it will observe, so that we can make that information available quickly for Webb. The By comparison, those two those little brown patch areas up at the top are the field that Kepler was able to look, and that was about 0.25% of the sky. So we're going to have a lot more coverage than was the case for Kepler. So this is a view of what the satellite actually looks like as it sweeps across the sky. And what you'll see in just a second, in fact you can see it now, are those faint beams that are sticking out. Those correspond to the fields of view from 4 cameras that are arranged so that they look at the sky from an area near the ecliptic, that's where the zodiac is, all the way up to that North Pole. And as you can see, the range is 96 degrees, the cameras are 24 by 24, and then what we do is we actually sweep that passband around the sky to make an entire map. And that takes about 2 years altogether. So this is the field of view that you would get from 1 out of the 4 cameras. It's 24 degrees on a side, and there are 4 charge-coupled devices. These are very special charge-coupled devices that were fabricated at MIT that have the unique property that they can see not only the light that our eyes can see, starting with the red band, but they also extend out to wavelengths about twice longer into the infrared. And it turns out that many stars, in fact the majority of the stars in our Milky Way galaxy, emit most of their light in that passband. So this is an area that really has not been studied at all with the type of sensitivity that TESS will provide. So what you can see is, to get an appreciation for this, is you could put 10,000 moons inside this field of view, including the fields of view of the other 3 cameras that would extend up another 4 stories above this. And this is where the Kepler field of view lies. And then these are actually 30-minute full frames, and it's just repeating what I said before, that we've got 30 million objects altogether that we can look at in that regime. And it finds a new section of sky that it looks at every 27 days. And what I showed you before was a simulation. This is a real image that we took by taking one of the engineering model cameras to the roof of one of the buildings at MIT on a really cold January night just 2 months ago. And we just looked at the zenith, and then this is what we saw. We estimate that, and this is just a portion of one image, this represents about 0.1% of the sky. And so what you actually see is there's probably about 100,000 objects in this. So if you extrapolate from that, that would mean that with this level of sensitivity, we're talking about somewhere between 500 million and 1 billion objects that you can see. Now we can't do precision photometry on the very tiny spots that you see corresponding to faint stars, but certainly for the bright stars, these 3 that you see near the top, those are stars that if you go out tonight and look at the zenith just as the sky is getting dark, you can actually see those stars as part of the constellation Auriga. These are 2nd magnitude stars. They're among the couple of hundred brightest stars in the sky. And so one of them, in fact, is what we call an M dwarf, and the expectation is that we're going to study that in great detail, and it's close enough that it could be followed up. And this is something that's really unique for TESS, because TESS on average is looking at stars that are about 100 times brighter than TESS. And so to me, one of the wonderful things about this mission is that we're going to actually be able to go out in the sky, and you or your kids or your grandkids or whoever, and you'll be able to point at one of these stars and say, there's a habitable planet associated with that, and who knows, another 30 or 40 years, we'll know exactly what the properties of whether there are any biogenic signatures from that planet. So this is an animation that just shows how TESS sweeps across the sky with those 27-day observations. We're going to do the southern hemisphere first, and then the northern hemisphere in the second year. And then what you'll see is that there's that area that's shown as a circle, which will turn color to orange, as I recall. And that is the area of where all of those little red dots were concentrated in that first image that we showed. So then I think this is an animation that shows if one were to look out from the solar system at successively greater and greater distances, what are the planets that TESS might be able to determine. This is a simulation. The image that I showed previously was a real image, but this is basically what you see, and it's going to go pretty fast, and you're going to see several types of dots. You're going to see orange dots that have been predicted for TESS, and then there's some objects that have been seen by other missions and ground-based work. So here we go. We're headed out. It's pretty fast. 3 parsecs, that's 10 light years. And then further and further, you see all the orange dots that are coming in. It's all orange dots, all orange dots.
Wow.
And then finally, you see a few blue dots going off to the side, and that's the spray of stars that have been studied by Kepler. But all the way in the interior region near the solar neighborhood, it's going to be all TESS all the time. So anyway, so this is another way of looking at that simulation that I think is really cool. This is distance along this axis, and the axis has actually been cut off. And the blue objects over here, this is out to the right of this is about 3,000 light years. And at the border where you start to see the orange dots come in, or the orange circles come in, that's where TESS is. And so you can see it complements Kepler very well because we're looking close by, and because the blue dots are 10 times more distant than the orange circles are. That means the stars are going to be 100 times brighter. And there's even some exoplanets that we show that are in the local neighborhood over here. The diameter of the circle just is an indicator of how deep the transit actually is. So this is another way of looking at TESS. This is the James Webb Telescope in the background, and the real question we're asking and answering with TESS in part is that where do we want to point this monumental telescope that's going to launch in 2020? And if this animation works, which it doesn't, you will see TESS, and that means that it's going to be basically the finder scope for JWST and all of the telescopes that are going to come in the future. So thank you very much for coming, and let's all cross our fingers and do whatever you can for good luck for tomorrow night. I think the weather's going to be great. The team is ready. Everyone has worked on this now for the last 5 years intensively on the hardware, and then the previous 8 years that we were working on the concept and studying it both at MIT and the other groups that are collaborating with us. The scientific team includes people from the Harvard-Smithsonian Center for Astrophysics and other scientific institutions at universities throughout the United States and throughout the world, and we're looking forward to an exciting time. Thank you.